Welcome back. Today we're going to be looking at section 5.2. This is a section over power functions and polynomial functions. These are two types of functions that have the same base or the same root. And essentially what happens is we went from linear functions, which is a power of 1, to quadratic functions, which is a power of 2, now to power functions, which is just any power, and then polynomial functions, which is add them all together. And so let's go ahead and get started. This is, again, section 5.2, so we're still pretty early in the chapter. We will jump right in. So power functions, other than having the word power in it, this is just a scripture of the day. A little bit of encouragement before we get started. Joshua 4:24 says that God did this so that all the peoples of the earth might know that the hand of the Lord is powerful, and that you might always fear the Lord your God. So just nothing to do with power functions or polynomial functions in general, but a good reminder of the power and the might of the Lord your God. Here we go. Let's jump right into it. A power function can be represented in this form. F of x equals kxp, or kx to the p, power. So then they're going to ask us, well, are these of that form or not? And if you look at these examples, you could say this is equal to, if you do some reducing based on the properties of exponents and the properties of like terms, 8x to the fourth. The next one, you might recognize, so is that a power function based on the kxp? It is. K would be 8, and x to the fourth. 4 would be p. This next one you might recognize as a polynomial. Notice it has two kxp terms, not one, and so it's not a power function. And this next one you may recognize, if you've seen anything like this before, as a rational, and so it's not kxp. So just a little bit of recognizing what looks like a power function. These power functions are really important because they tell us about the end behavior of a graph. Specifically, when it's just one term, it's the end behavior and the whole behavior of that power function. But as we build polynomials out in the same section, we'll see that this is all about end behavior. And so here's what I want to draw your attention to. Evens do the same thing. The most basic even function in the world, you can think of like x squared. X squared looks like that parabola. And so even functions look like a parabola at the beginning and the end. If it's even and positive, it goes up. I would say that's like a happy parabola or a positive parabola. The concavity is positive. And if it's even and negative, it goes down, like a frown. So you've got even powers going the same direction, and I always do it with my hands. Even positive, even negative. And then you've got odd powers. Think of the most basic odd function there is. I would call that like y equals x. And I guess I could have called this y equals x squared. Y equals x looks like a line. The end behaviors, the things that happen on the far left and far right, are doing something opposite. And if you look at these two end behaviors, we've got, again, a positive version and a negative version. Those, instead of thinking happy and sad, like a frown or a smiley face, think about your bank account. Which one of those looks like the better bank account to have? The positive one certainly looks like the bank account you want. And so positive means it's increasing as x gets bigger, and negative means it's decreasing as x gets bigger. Sweet. So that's the end behavior. So here we go. We are going to determine the end behavior and describe it. So here's where I'm going to show you where to look for this positive, negative, even, odd. So for the even, odd thing, we're going to look right here. This yellow highlight, well, I'll make it green. This green highlight is going to tell us even or odd. And because it's even, it gives us that our behavior is either up like this or down like this. We haven't decided which one yet. That's going to be based on the positive or negative. And so then we look at the beginning of the a value, or the beginning of the term, and we say that negative sign means that we are going to pick the sad looking one, because it looks like a negative, a frowny face, if you want to think of it that way, concave down. So Where do we look for even or odd? Look to the power. Where do we look for happy or sad or negative or positive? Look to the coefficient. So we're going to describe it in symbols, and that's just to say, okay, this is what my graph looks like. Oh no, it's going down. We just said that. This is what my graph looks like. And so on the left here, I'm going to say as x approaches negative infinity, which pictorially what that looks like is a guy, and he's walking towards negative infinity. So if you start at 0 or in the middle, you start walking towards negative infinity, what happens to that guy? His y value? Y approaches negative infinity. But if you take that same guy and you start walking this way, so we'll say as x, go up here, as x approaches positive infinity, which would be that same guy walking this way, he also goes down and falls off the graph. Y approaches negative infinity. So no matter which way the guy goes, towards negative infinity or towards positive infinity, he approaches negative infinity on the y-axis. All right. Now, the only other thing to add is that we can just add these things together or subtract them. We can add and subtract all of these power functions to make a really long polynomial that looks like this. And the one thing to note out of the polynomial is that leading term, because that leading coefficient and leading degree are still going to tell us the end behavior. And so here is a polynomial. Before even starting any problem, I like to rewrite it and make sure you have decreasing powers. So negative x6 plus 4x squared plus 2x minus 6. This was just a rewrite with decreasing powers so I could go to the front and highlight my leading term. And I'll answer the 3 questions that they give me. What's my degree of this polynomial? That just means the highest exponent. So you have 6. What's the leading term? That just means the whole highlighted term, including the coefficient, the sign, the variable, and the power. And so that's just going to be negative x to the 6th power. Degree, leading term. And then what's my leading coefficient? It's got a little bit tricky because it's a little invisible, but it's just that -1 that's out front. And using the degree and the leading term and the leading coefficient, we're going to be able to find our end behavior, just like that chart above. Okay, so because they just jumped straight to a graph, let's go ahead and find it. We don't know a lot about this graph, but what we do know is that at the very ends of the graph, that leading term is going to tell us it's even. And then we take that negative sign, apply it to the even, and say, what does it look like for something to be negative and even? It looks a little bit like that. So we don't know a lot about this function. We don't know what happens in the middle. But what we do know is at the ends, at the far left and the far right, it's going down like that. And that comes from the degree, the leading term, and the leading coefficient. Cool. So then working a little bit backwards, they give us a graph and they say, determine a possible degree of the function. And so to do that, I need to look at this and say, are they going the same direction or are they going opposite directions? They're going opposite directions, so your degree could be 2 or 4 or 6, ... All we know is it has to be even. And then the end behavior that they ask us for in the problem, we're going to write that same type of notation with the arrows, where we say we look at this arrow, and we say as x approaches infinity, or as that guy walks to the right, y approaches negative infinity. Again, what that means is you have a guy standing on it, and as he stands on it and he walks towards infinity in the x direction, he goes down. And as he walks towards infinity in the y direction, he falls down. So we use this arrow to say as x approaches negative infinity, y approaches negative infinity. There's the difference between those two. The blue arrow is telling us the blue end behavior, and the red arrow is telling us the red end behavior. Just some names for these things that we've been talking about. We've got turning points, which are maxes and mins, local maxes and mins. We've still got x-intercepts, which you've seen 3 or 4 times now. You've got y-intercepts. And you've still got, even though it's not labeled, these 2 arrows talking to you about end behavior. So I know it's not labeled, but I think it's worth noting because that's all we've been talking about today. Those arrows tell you a little bit about your end behavior. And here we go. They're just going to ask us to find the intercepts, which is using the same skills we've been using in this class to find intercepts the whole time. So let's do it. The first thing we're going to do is find y, because like I said, I always think that y is the easiest intercept. You just say, what's f of 0? And if you plug and chug 0 into this function, f of 0 equals 0 minus 0 minus 0 if it's plugged into all those x's. And so f of 0 equals 0. Now we're going to take the x-intercept, and we're going to say, how do we solve for that? We say f of x is equal to 0. And so we say 0 equals 2x to the third minus 6x squared minus 20x. And we got to go slow, and we got to solve this. It looks like we're probably going to do some factoring out first, and it's hopefully going to make us an easy factor, or an easily factorable quadratic. So the first thing I'm going to do is I'm going to take out something that's in common with all 3 terms. And so 0 equals 2x on the outside. And what do we have left on the inside? X squared minus 3x minus 10. Redistribute it to check and see if you're right. 2x times x squared is 2x cubed. So the first one's right. 2x times negative 3x is negative 6x squared. So the second one's right. And 2x times negative 10x is negative 20x. And so the third one's right. And so we have one of our factors right here in red, and we're going to get the other 2 by factoring the blue, which would be negative 5 and 2 add up to give you negative 3. And so we have 0 equals 2x times x minus 5 times x plus 2. Which means each of those factors, using the 0 product property of multiplication, gives us a 0. X equals 0, x equals 5, and x equals negative 2, which in turn, don't forget what they asked us for. They asked us for our x-intercepts. And so that would be 0, 0, 5, 0, and negative 2, 0. And they asked us for this y-intercept up here, so we'll bring that down, and we'll say 0, 0 is our y-intercept. And we have the 2 things they asked for. Y-intercepts in red, and x-intercepts in blue. And you'll notice 2 of those are the same. That means it crosses x and y, the x-axis and the y-axis at the same point, which is pretty interesting. All right, let's keep rolling. Now we're going to see just a quick little fact. A polynomial of degree n will have at most n x-intercepts. N was the degree. So degree tells you at most, or the max x-intercepts, and subtract 1 from that for the max turning points. So in short, n equals degree, which equals max x-intercepts. And n minus 1 equals max turning points. And so here's a function, and it said determine the maximum number of x-intercepts. So we're just going to look at the biggest power. Looks like it's right there in the middle. And so max x-intercepts is literally 12. That just came from the biggest degree we have. And then if we look at the formula for max turning points, max turns is 11 because we just subtracted 1. So just a little fact about these graphs. Remember, they look like this. And so we've got some that turn around and some that only turn around once and some that turn around a whole bunch of times. But the maximum number of times that specific graph can turn around is 11, and the max times it can cross the x-axis is 12. And so we're going to use all these skills and a graph they give us to say, what can we conclude about this polynomial? Well, right here, 1, 2 turnarounds. So 2 turning points is something we know. What else do we know? 1, 2, 3. 3 x-intercepts. And so what we can say is the degree is at least 3 or bigger, because that's what it said, is the degree was the maximum number of turning points. And we actually know something else about the leading coefficient. Based on the end behavior, this looks like a bank account going up or down. And is that the way you want your bank account to go, to start really high and end up low? No. And so that means A is negative. So we know the degree is greater than or equal to 3. The leading coefficient is negative. And there's actually one more thing we could say about this. And it's also about the degree. We know that the degree is odd based on the fact that those end behaviors split. Remember, evens would go the same direction. It would look like that. Or that. Evens, they end going the same direction. Odd, they split. So even up, even positive, even negative, odd positive, odd negative. Kind of a way to remember it on one hand. You can do even up, even down, odd up, odd down. Cool. There's probably a lot more we could talk about that graph. We could actually give them what the x-intercepts are. We could probably give them what the y-intercept is. We could probably tell them a little bit about the local mins and the local maxes. So based on all the things we've done in this class, there's a ton we could do with that graph. We could write a whole paper about that graph saying we know about local mins, we know about absolute mins, we know about x-intercepts, y-intercepts, and how to find them. We know about the max number of turnarounds points, like we've just said in the last problem. But this question literally just asks us for intercepts and turning points, and so that's what we did. All right, so last is just, here's a function. Let's find everything we can. So we'll do this carefully and a color at a time. So we've got y-intercepts being the first thing they ask us for. Remember, that is just f of 0. So we'll do that over here, and we'll say f of 0 equals 0.2 times negative 2. I went ahead and evaluated 0 minus negative 2 for you. 1, because 0 plus 1 is 1, and negative 5, which is just equal to 0.2 times 10, which is just equal to 2. And so what's your y-intercept? Remember, 2 isn't a y-intercept. The y-intercept would be 0, 2. All right. We did one thing they asked for. Second thing they asked for, x-intercepts. And the nice thing about this is they've already factored it for us. We don't have to do the hard part of factoring. X-intercepts just come from f of x equals 0. And so we say 0 equals 0.2, x minus 2, x plus 1, x minus 5. And we have it already factored out. So we just set each of those x's equal to 0. So x equals 2, x equals negative 1, and x equals 5. From each of those factors, all factors give you a 0, and so each of those factors gives us a 0. And so we have the x-intercepts of 2, 0, negative 1, 0, and 5, 0. And those are your x-intercepts. Next, they ask us for end behavior. Make this green. And for end behavior, I'm going to look up at the function, and I'm just going to look at what the degree of the function is. And this one's a little tougher to see because I don't want to necessarily FOIL it all out and get one long polynomial. I just want to look at the power associated with each x value. And so even though it was invisible, there's technically a power of 1 up there. So each x value has a power of 1, And how many x's are there multiplied by each other? There's 3 x's multiplied by each other. And so the leading term, if you were to multiply all of that out, would be the leading. This is why that one question asks us for the leading term, because it tells us so much about the graph. The leading term would be that 0.2a value times x to the third, because there's 3 x's there. And if you don't believe that, looking at that power tells you that, you could multiply it all out using FOIL, the first, outer, inner, last method, and work through that problem. But the leading term is that, and then after the leading term, you have a bunch of stuff added to it. But we don't care about that bunch of stuff added for the end behavior, because the leading term tells me the degree is odd, and a is greater than 0 or positive. An odd positive looks like a bank account that's going up, so it's going to look like this. So the end behavior looks like that kind of curvy line with the dots in it. And we'll say as x approaches negative infinity, y approaches negative infinity. And as x approaches infinity, y approaches infinity. That's the 2 ways that x is working. Remember, that's the guy walking again. If you're like, whoa, we're doing a lot, that's the guy walking. And as the guy walks towards infinity, he goes up. And as the guy walks towards negative infinity, he goes down. And the last thing they asked us for is the number of turning points. And remember, the turning points, that was a pretty easy one to do. You just take the degree, number of turning points. You just take the degree and you subtract 1. And so what was the degree of this function? It was 3. That was the odd power in the leading term. And so it has at most 2 turns. And there are the 4 things they asked us for: the x-intercepts, the y-intercepts, the end behavior, and the turning points. So that's an introduction to power functions and polynomial functions. In the next section, we're going to look at the graphs of these things, so we'll get to put these principles, these same 4 principles that we just did, on a graph and see how it affects the graph. I would encourage you to keep working through the blank notes, the completed notes, watching these videos, and reaching out to your instructor if you have any problems at all. Thanks for watching. I'll see you next time.